Welcome to the class. Dear students, today we are going to discuss on polarity and dipole moment. So first we will discuss about what is polarity, then we will see what is dipole moment, and then we will see the conditions for polarity. What are the conditions of polarity? What conditions a molecule should fulfill in order to be polar? We will see those conditions with examples. And lastly, we are going to see the significance, the impact of polarity on a molecule's physical and chemical character. So let us start the class. Polarity. So polarity is separation of electric charge in a molecule. It is separation of the electric charge. See, separation of electric charge in a molecule, or separation of positive and negative charge in a molecule. Now the question arises, why this positive and negative charge arises in a molecule, or it comes in a molecule. So for that we have to see what is covalent bond, how a covalent bond is formed. So a covalent bond, as you can see here, when two atoms, they come close to each other and they combine with each other. And how they combine with each other? By sharing their electron. They go for mutual sharing of electron, and this mutual sharing of electron results in a covalent bond. Okay, so here one hydrogen combines with another hydrogen and they go for a mutual sharing of electron and they form a covalent bond. Okay, now in this case, in hydrogen's case, the mutual sharing of electron is equal. Okay, that is, it is equally shared by the two atoms. Okay, now in some cases, in other cases, when two atoms combine, okay, they form a bond by sharing their mutual pair of electron. Of course, it's as the same like this, and this is done in order to complete its octet or duplet configuration, and in that way it forms a covalent bond. But however, here in this case, in the case of HCl, the shared pair of electron is not equally shared. The shared pair of, yes, there is mutual sharing of electron, but it is not equally shared. Why does that happen? Why in H2 it is equally shared and why in HCl it is not equally shared? In H2, both the H are of same electronegativity. Okay, they are having same electronegative nature, they are electropositive actually. So they are same magnitude of electropositivity. But in case of HCl, there is a difference in electronegativity of the two atoms. And because of this difference, because of the difference of the power of withdrawing electron towards itself, that is what is electronegativity. Because of that difference, the electron cloud gets shifted towards the more electronegative atom. The electron cloud gets shifted towards the more electronegative atom, resulting in a negative charge around the electronegative atom. That results, that shift towards the more electronegative atom, that shift towards the atom that withdraws the electron, that shift results in a negative charge around the region near the electronegative atom. And of course, this results in polarity. Such a bond is called as a polar covalent bond. Such a bond, because it is polarized, right? The electron cloud is not equally shared. The electron pair is not equally shared. It is shifted towards the one which is more electronegative, and that results in polarity in the molecule, right? That results in development of a negative charge around the area of the electronegative atom. That results in polarity. Such a bond is called polar covalent bond, and such a compound is called polar compound. Vice versa, the vice versa case, we have seen, if two atoms of the same electropositivity nature, if they come and combine with each other, if they share their electron, the electron pair lies at the center. The electron cloud is evenly distributed, and such a bond is non-polar covalent bond. Such a compound is called as a polar covalent compound. So it is basically what we infer, what we conclude from this is that it is because of the difference in electronegativity of the combining atoms that polarity results. It is because of that difference only that the electron cloud is shifted towards the more electronegative atom. It is because of that difference only that polarity results. That polarity results. Now, let us come to dipole moment. Then what is dipole moment? Dipole moment is the measure of this polarity. Dipole moment is the measure of the polarity. Exactly how much strength that does this polarity have, exactly how much polar it is, that is expressed, that is referred to as dipole moment. That is referred to as dipole moment. So dipole moment is represented by mu. It is represented by mu, and its units is called as dB. It is called as dB. Okay, so dipole moment is giving you exactly quantitatively how much powerful is the polarity, how much is the strength of that polarity. It is represented by mu and its units are dB. Now how it is given, let us see that how it is given. Okay, how it is calculated. dB is calculated as charges. Okay, charges of the atom, charge of atom, charges of atom, which atom? Combining atoms, yeah, charges of atoms, that is Q. Okay, that gives you electronegativity difference. Okay, so that is electronegativity difference into distance between positive and negative center, distance between center of positive charge and center of negative charge, center of negative charge. This is D. Charges between molecules. Okay, this is right, this is a HF, this is a no, this is a polar covalent bond. The charges, okay, so that is the electronegativity difference. This is right, this is +1, so that is the electronegativity difference, the charges of atom. And one more thing, what is that thing? The distance. Look at the distance between H and F atom, the distance between center of positive charge and the center of negative charge. So that is interatomic radius, correct? That is also called as interatomic radius. So it depends on, that is represented by D, this is represented by Q. So the dipole moment is a product of, it is a product of the charges, that is the electronegativity difference, and the distance of the distance between center of positive charge and the center of negative charge. This is nothing but interatomic radius. It depends on both of these. It's a product of both of this. But one thing I would like to tell you, my dear students, that it primarily depends upon only this electronegativity difference. This has a lesser impact on dipole moment. Why this has a lesser impact? Because as you go down a periodic table, or as you go from left to right towards a periodic table, or as you go down towards a periodic table, down on the column, the distance does not increase so gradually as the charge increases. You got it? That as you go down, let's take the example of halogen. As you go down from F to Cl to Br to I, right, the distance between H and F, or H and Cl, or H and Br, or H and I, it does not vary so significantly as electronegativity varies. So the dipole moment primarily depends upon the charges or the electronegativity of the atoms, and secondary impact is on distance. That is only a less impact. Okay, this has a much greater impact. Let us understand this, what I have said, by looking at the dipole moment of HF, HCl, HBr and HI. So for HF, we are having dipole moment 1.75 D. Okay, for HCl, our dipole moment is 1.03 D. For HBr, we are having dipole moment of 0.85 D, and for HI, we have a dipole moment of 0.38 D. So this is the dipole moment. Dipole moment is nothing but a measure of polarity. That means as the dipole moment increases, polarity should increase. So let us see how the dipole moment increases this way, right? So mu increases like this, dipole moment increases like this, fine. So and polarity also increases like that. As you go up the table, polarity increases, dipole moment increases, okay. And what about electronegativity? Electronegativity also increases like this. Electronegativity increases like this, right? So electronegativity increase. Of course, there is electronegativity difference between HF, but that much difference is not there between HI. HF bond, there is the high electronegativity difference, correct? And what about interatomic radius? Interatomic radius increases like this. Interatomic radius, that is D, it will increase like this. So I have drawn this table. See the polarity, which is the most polar? HF is most polar. Which is the least polar? HI is the least polar. Which is having more dipole moment? HF is having more dipole moment. Which is having the least dipole moment? HI is having the least dipole moment. So which one is more polar? HF is more polar. What is the reason of polarity? The difference of electronegativity. That is, charge is the reason. Q is the reason, right? So Q is the reason that it is more polar, that it has got a higher dipole moment. But if you think the other way, see the interatomic radius here is less, right? Both H and F are small atoms. The distance between positive center and negative center is less. Here the distance is high. It is having a large atom. So it is high. The interatomic radius or the distance between the positive center and the negative center is high here. So what is our dipole moment formula? Q into D. For this, Q is less, but D is high, correct? But for HF, the Q is more and D is less, right? So the impact of Q is more, okay? The impact of electronegativity difference is more, and that is why the dipole moment for HF is more, okay? D is increasing, of course. If you are going from HF to HI, D is increasing here. The interatomic radius is increasing here. But that increase of the interatomic radius, that increase of the distance between the positive and the negative charge, that increase is not able to compensate for the increase in for the decrease in electronegativity difference. See, here there is increase in interatomic radius, but that increase in interatomic radius, it is not able to compensate for the decrease in the electronegativity of the atom. Electronegativity of the atom. Here there is a decrease in the interatomic radius, but that doesn't matter because there is a significant electronegativity difference in HF, and that results in a higher dipole moment of HF. That is why I was saying that in dipole moment the formula is charge into distance between positive and negative center, but the charge has primary impact. The distance, it increases, of course, as you go down the table it increases, but that increase is only marginal compared to the electronegativity difference. So the electronegativity difference primarily determines what the dipole moment will be. Therefore, we are getting readings like this. Okay, I hope you have understood this concept. This concept is very important to understand. Dear students, now let us see conditions for polarity. Okay, let us see conditions for polarity. Conditions. Our first condition, of course, you can judge by yourself. At least one should be polar. At least one bond should be polar. At least one bond should be polar, right? At least one bond. Of course, there can be 2 or 3 bonds polar. We don't have a problem with that. But at least you should have one bond that is polar. See, look at this methane. Look at the methane molecule. Is it polar? Not at all. No doubt. It is non-polar. This methane is non-polar because not even one of its bond is polar. Not even one of its bond is polar. Now, this is at least one. So there can be one or more than one. More than one. There can be more than one. But in that case, you have to see net polarity. Net polarity. Okay. You have to see net polarity. Okay. You have to see the shape of the molecule. And you have to see the net polarity. Let me give you an example. See, look at this. This is water. How many polar bond the water has? 2. Right? How many it has? 2. So, look at this. Let me tell you one thing which I forgot to tell while I was mentioning dipole moment. Dipole moment is vector quantity. Vector quantity means it has got a magnitude and it has got a direction. Suppose this is the dipole, okay, we are taking HF as example. This is of course a dipole. This is the positive center, this is the negative center, this is of course a dipole. Now there is a magnitude, okay, and the direction is from center of positive charge to center of negative charge, okay. So direction is from the region from where the electron density has been taken to the region where the electron density is there. So that is how a dipole moment is expressed. It is a vector quantity. Okay. So here, if you are drawing the vector towards where it will come, like this. Correct? Like this, the dipole moments are there. They are both in same direction only, not in opposite direction. They are both in same directions. Correct? So they won't cancel each other. Fine. So there are more than one bond, right? There are more than one polar bond and there is a net polarity because they don't cancel each other. The shape of the molecule is such that they don't cancel each other and therefore the water is polar compound. It's a polar compound. Fine. Now take the example of carbon dioxide. This is carbon dioxide. What about this? How many polar bonds? 2 polar bonds. And how will you draw the dipole? Dipole is like this. It's going like this and from here to here. Look. They are in opposite direction and they are of the same magnitude. So they would cancel out each other and the net polarity will be 0. So dipole moment here will be 0 mu. Correct? 0 mu. Let me draw another molecule to give you further example. Look at CCl4. Cl. Look at this CCl4. What is a dipole moment? How will you draw that? See here. This one's here. This one's here. And this goes down. See, this one cancels this one. This one cancels this one. They are of same magnitude but they are in opposite direction. So the net dipole moment here is 0. Net polarity is 0. Let me take one more example. This is tetrachloroethylene. Tetrachloroethylene. Look at this. Tetrachloroethylene. It goes like this. Fine. Dipole moment in this direction. See, dipole moments are in opposite direction. This one cancels this one and this dipole moment cancels this dipole moment. So the net dipole moment, the net polarity here is also 0. So these are examples of compounds where there are more than one bonds, but the overall polarity, the overall dipole moment still is 0 because they cancel out each other. Why is it so? Because the geometry or the shape of the molecule does not permit polarity. The geometry or the shape of the molecule does not permit polarity. A linear compound, see, This was linear, carbon dioxide. This shape does not permit polarity. Okay, a tetrahedral shape also does not permit polarity. We have seen a tetrahedral shape when we were seeing carbon tetrachloride. See, this is a tetrahedral shape, right? This also does not permit polarity. This will be like this, but they will be of course in opposite direction. This does not permit polarity. So a tetrahedral shape, a linear shape of the molecule, it does not permit polarity. The shape or the geometry of the molecule should be such that it permits the polarity. So these are two conditions. There is a third condition also. There is a third condition. You can also include geometry or the shape of the molecule, that point here. There is a third condition also, hybridization. What kind of hybridization? Hybridization, it also affects polarity. Okay, normally what this thing is that sp hybridized carbon atom is more polar than sp2 hybridized carbon atom, that is more polar than sp3, which is not at all polar. It's not at all polar, but the sp hybridized carbon atom has got polarity. It has got polarity. Okay, why so? There is an explanation for that. It is because, see, in S there is 50% S character, 50% P character. So the hybrid orbital, the hybrid sp orbital, there will be two orbitals. The hybrid orbital will be more spherical in shape, more spherical, because it has got 50% S character. So the hybrid orbital will be more spherical in shape. More spherical in shape means, what is the meaning of that? That it will be much nearer to the nucleus. It will be much nearer to the positively charged nucleus. So this positively charged nucleus can would have more electronegativity, right? The net effect, the net positive effect, the effective positive charge here of this carbon increases, because the hybrid orbital that is formed is spherical, it is small, and it is near the nucleus. So the effective positive charge, okay, that carbon nucleus exerts is much more. So therefore it would be able to attract electron, right? It would be able to attract electron towards itself. So that would increase the electronegativity of sp hybridized carbon atom. Therefore sp hybridized carbon atom is polar. It exhibits polarity, correct? sp2 also exhibits polarity, sp3 doesn't. So sp2 and sp carbon atom exhibits polarity. I hope you understood. Why? Because S 50% S character, P 50% P character. So the hybrid orbital formed will be more spherical. It will be nearer to nucleus. Now the carbon can exert its positive charge effectively. It can attract electron towards it. That would make this sp hybridized carbon atom electron negative. So an sp hybridized, because it has got more of S character, has more polarity. It has more electronegative than a sp2 carbon atom, which is less electronegative than a sp3 carbon atom, which is not at all negative. So sp carbon atom has the capability to exhibit polarity. So this is what is proved. This is proved when we are seeing toluene. So this is toluene. All are carbon atoms in toluene, but there is a polarity which is exerted downwards, and this polarity mu is 0.34 dBi. 0.34 dBi, correct? 0.34 dBi. It's why? Because there is this carbon atom is sp2 hybridized. This carbon atom is sp2 hybridized. So that is why there is a polarity of 0.34 dBi. So this is these are the four conditions of your polarity. Now let us go for significance of polarity. What is the significance? What is our use of knowing this? See, the first thing is that you can determine the geometry or shape of the molecule. right? You can get an idea of what is the shape or geometry of the molecule. You can determine the arrangement of bonds in a molecule. Arrangement of bonds in molecule. Am I right? Yes. See, we already discussed that if the dipole moment is 0, even though it has got number of multiple bonds, if the dipole moment is 0, that means the shape of the molecule is not permitting it. We have seen that dipole moment is 0 for linear molecules, for tetrahedral shape. So if we get a dipole moment 0, then our molecule may be linear in shape or it may be tetrahedral in shape. Also we will get an arrangement of the bonds. We get to know about the arrangement of bonds, how it is arranged. So we can determine this. The second thing is we can determine ionic character in a molecule. Yes, I of course agree that we are talking about covalent bonds. This is but a polar covalent bond. But the polar covalent bond, if the polarity is very high, if the dipole moment is very high, then it can exhibit ionic character. Am I right? It can exhibit ionic character. For example, HF. The polarity is so high. It is so high. 1.75 dB is the dipole moment. The polarity is so high that it exhibits ionic character. It exhibits ionic character. Correct? So ionic character it can exhibit due to the high polarity. It would go for reaction, ionic kind of reaction. Formation of ionic bonds will take place. So ionic character can be determined if we come to know about the polarity. If we come to know about the polarity. Third thing, we can know whether we can distinguish between cis and trans isomer. Cis and trans isomer. Okay, let me draw an example and tell to you how. See, this is a cis isomer, fine, and this trans dichloroethene and cis dichloroethene. This is cis dichloroethene, this is trans dichloroethene. There is a dipole moment in cis dichloroethene, am I right? But is there any dipole moment in trans dichloroethene? No. They have magnitude, same magnitude, but they are in opposite direction. They would cancel out each other. So the net dipole moment here will be 0. But the net dipole moment here will be having some value. It will be having some value. So you can distinguish whether you have got a cis isomer or a trans isomer at your hand. So you can distinguish that. The fourth application of this is, can anyone tell? Anyone tell? Is there any idea? Hydrogen bonding. HF shows the highest hydrogen bonding. The hydrogen bonding value is more in HF, but it's not the case with HI, right? HF shows after that HCl, then HBr, in this order. So the intermolecular hydrogen bonding increases for HF, right? It is more for HF. So polarity can determine hydrogen bonding, right? It can determine the energy, the intermolecular hydrogen bonding, and hydrogen bonding can determine what? The melting point, the boiling point, right? Hydrogen bonding can determine the boiling point. It can also determine the solubility of compound in solvents that exhibit hydrogen bonding. The solubility of compounds that forms hydrogen bonding with solvents that exhibit hydrogen bonding. For example, HF. HF is more polar, its polarity is high, its dipole moment is 1.75 dB, its polarity is high. So it exhibits higher hydrogen bonding with water. So it is more soluble in water, correct? Because the dipole is more strong. So it will be attracted in a more strong manner with water. Okay, but in the other hand, HI will not be attracted so much with water because the polarity is less. So the hydrogen bond formation will also be less. So it determines the intermolecular hydrogen bonding energy, and intermolecular hydrogen bonding energy, it determines boiling point and also solubility of that compound in solvents that exhibit hydrogen bonding. Dear students, if you want to know what is hydrogen bonding, please do refer my earlier video in which I have explained hydrogen bonding in detail. So this is hydrogen bonding. And one more thing which is contradictory is acidity. Okay, it is acidity. See, this is the fifth thing, acidity. HF, HCl, HBr and HI. Which is the most polar? HF is the most polar. Which is having most dipole moment? This is having the highest dipole moment. This is having the higher polarity, very high polarity, 1.75 dB. Which is the least polar? This one. What is its dipole moment? 0.38 dB. So which will exhibit more acidity? By this convention, if we are looking through this lens, if polarity is increasing, then acidity should increase. H plus should go rapidly from this, but it is not so the case. Okay, the most acidic among these is HI. Okay, this is because this is having shorter bond length. HF is having shorter bond length. So shorter bond length means it is more close, the nucleuses are more close. Okay, so they are more attracted. The influence of nucleus, the attraction of nucleus is much more high. Okay, so that brings them together. They are polar of course, but its dissociation is hard. Here the bond length is more. Bond length is more means it can be easily broken. The energy of the bond is less. Okay, even though the polarity is less compared to HF, this can be broken very easily. So here bond length determines acidity. Okay, it's not that the polarity determines acidity, it is the bond length that determines acidity. So here the bond length is more, the bond can be easily broken, H plus can easily dissociate. Here the bond length is less, it is having more bond energy, so it is difficult to break HF. Even though the polarity is high, it is not able to, that increase of polarity is not able to compensate with the decrease in the bond distance or the increase in bond energy. That is not able to compensate for the increase in bond energy. So that is why acidity increases as you go down. Dear students, I hope you have liked and you have enjoyed the class. If you have done so, please do not forget to subscribe the channel. Please do share it and please do like it. Your small support will be a big encouragement. Thank you very much.